Good afternoon, everybody. Welcome to the MTL Seminar Series. And today we have the pleasure to have as a speaker Dr. Guohan Hu from IBM. She has degrees from Tsinghua University and Cornell on economics and material science. And she is a principal staff member of IBM and also the manager of MRAM. So she's a world expert on magnetic memory, and we are very honored to have her here. So without further delay, the stage is yours, and welcome.
Thank you all for attending and during the lunchtime. And good afternoon, everyone. It's a great pleasure to be here. I had a very short visit and talked to a couple of professors here in the morning. I was really, truly impressed by the depth and also the breadth of the research work here. So today I'm going to tell you a little bit about the the pointer doesn't work. Tell you a little bit about one of this emerging memory. It's called STT-MRAM, spin torque transfer MRAM. And to make a technology work, there are many different pieces, design, fabrication, materials. And for me, I have a materials background, so I will give you the materials perspective of this technology today. And I think you can feel free to ask questions if you have any during this talk. It's kind of slow. Sorry, I pushed the wrong button. OK, so here's the outline of the talk. So first, I will talk a little bit about what MRAM is, just to bring everybody to the same page in case you are not familiar with this field. Then I will focus on the spin torque transfer MRAM. So this is really the field that people are intensively looking into and where it's going to make the technology happen. For that part, I will also talk about the basic concepts, again, to bring everybody to the same page. And then I will focus on the major materials breakthroughs that enabled this technology today. So in a way, we are very close to a product. So I want to tell you what the materials breakthroughs that really enable us to get to this far. In this part, I will also talk about the work at IBM, where we focus on reduce the device switching current, reduce the power. Close to the end, I will also give you a view of where we are as a technology. And then I will summarize. So here is a very basic introduction on what MRAM is. So right now, in the known technology, we have the silicon technology. This is the CMOS-based work, and everybody knows and use. And then we also have the magnetic film technology, known as the hard disk drive. You may not be that familiar with that anymore, depending on your age. But this was a big industry, and it still exists. And still, I have a hard drive in my laptop. So they use magnetic films, and then MRAM usually combine the two together. So we use magnetic films for the storage element, and it combines with the CMOS technology. Also, this creates some of the problems. So there's domain knowledge-wise, the hard disk drive people, they know a lot about magnetics, but they don't really know much about CMOS. And the CMOS people know a lot about CMOS, but they don't really know much about magnetics. So you really need to bridge the two together. And this is MRAM. I will show you schematics later on. You can see the two pieces we have in the memory one is a magnetic tunnel junction, comes from these magnetic thin films, and then another one is the transistor. So that's the two key components. So you really have to combine the two together. And when we combine them together, among these all emerging memories you may hear of, and I will touch upon a little bit, this is the only scalable memory. Means you can really go down the sides instead of stop at one generation. And then that combines non-volatility because it's using magnetics, and with the high endurance. It's also because you are flipping spins instead of moving anything physical. So that really gives you a lot of advantage compared to most of the emerging memories, which I will show in the next couple slides. So here are the different types of MRAMs we went through as an industry. So the study actually started very early on, like early 1990s. And when you think about anything magnetic, one easy thing, if you want to manipulate the magnetization, it's field, right? This has been known for 100 years, and that's where people started with. So when you combine with the CMOS, you don't really want to use electromagnet try to manipulate the magnetization by generating field. So what people do is you can send the current through your wires. They will generate oscillator field. So you use this oscillator field generated by current to switch your magnetic entity. And this research was going on for about 10, 20 years. And there are products on the market. You may not aware of it. So for example, Aerospin, they have been shipping this field MRAM for many years now. It's very niche in the market, but there are products existing using the field MRAM. So one of the big problems with the field MRAM is it does not scale. So when you go to smaller bits, you need even higher field to switch it. That means you need even higher current to generate those fields to switch it. And when you think about the CMOS scaling rule, when you go to a more advanced node, the current the transistor can apply actually decreases. So this does not go together. So that's why the research, I think, ended about really a couple years ago, about 5, 10 years ago. So they're still making this field MRAM product because it has its own advantages, but we don't really see a path to scale down. So from like early 2000 to today, so what people have been focusing on is this so-called spin torque transfer MRAM, where you use the current to write your bit, which I will touch upon in the following slides. So if you look at the structure, it's very simple. So you have a magnetic tunnel junction, and then you have a transistor. That's all you have. So the structure-wise, it's very simple, and you can scale it, and you can pack them very dense when the structure is simple. And also, one good thing about this structure is the current actually decreases when you go to smaller bits, because the current density is fixed. So when you shrink down your size, the current itself actually decreases. So it really goes along with the silicon scaling trend. So that's why it attracts a lot of attention. And people have shown you can scale down to 10 nanometer size, and the physics still works. You just need to work out other engineering part of the device, which I will also show later on. So here some basic information about spin torque MRAM. I touched upon a little bit already. So this is schematics. I said earlier on, it's a very simple structure. So your memory element is a so-called magnetic tunnel junction, and then you have a transistor. So the read and the write was done the same way. You just pass current through your MTJ by the transistor. And when you write it, you need a higher current. When you read it, you use a lower current. It goes bipolar to go from 0 and 1. So for the memory element, so we call it the magnetic tunnel junction. So it is a tri-layer structure. In the simplest case, you have insulator in the middle. So this is what we call a tunnel barrier. Then you have two ferromagnetic electrodes. So one of them is called the reference layer or fixed layer. One is called the free layer, which is switchable. So during the operation, the reference layer or fixed layer stay put. So the magnetization does not change at all. It's the free layer, you can flip it up or down. So then when you compare the configuration, if they are anti-parallel to each other versus parallel to each other, the resistance will be different. So this gives you the memory state of 0 and 1. And you can imagine you want this difference to be as big as possible. And then otherwise, you will have a problem when you read. So imagine, so one single device is OK. You have one state here, one state here. Right? One is low, one is high. But if you have a memory device, you have million bits or gillion bits, and then you billion bits, then each will have a distribution, can you imagine, right? Then if they are not further apart, the distribution will kill you. So they will merge together. You will never be able to read what's a 0, what's a 1. So that's why there's one important figure of merit for this magnetic tunnel junction. We call it tunneling magnetoresistance. So it's defined this way. So it's the difference between the high states, the difference between the two resistance states over the low resistance states. And you want at least something around 100% right now. I mean, the way they define it, basically off and on ratio of 2. If you think it's in the other memory language, it's fairly low actually, the requirement to make this work. So this is the basics on the switching mechanism. So you have your fixed layer, your free layer, you pass the electron through. So this electron carries this angular momentum for your fixed layer to the free layer, then it can make it switch. So the switching is not, it's something like this. So this is the magnetization of your free layer to begin with. And depending on what kind of current you give it, then it switches differently. The trajectory can look very different. For example, if you have a free layer pointing to the North Pole to begin with, and you give a current to try to switch it, if the current is very small, you just knock it off from the North Pole, then when you take off the current, it eventually damps back to its original state, so there's no switching. Or if you give it a little bit larger current in the green case, so it starts to process very, very, very slowly. If this is barely, sometimes they barely make it, and then this is your so-called critical current. That's when you can make switching happen. If you want to make it switch fast, you just give it more current. So this is the red trajectory. So if you dump in a lot of current, it can switch very fast. So you can see there's a trade-off there already. You can make this device switch very fast. You just have to dump in more current. So then the optimization is really how do you get the fast switching but use the least current. So that has been the game of the field. And here just one example to show this is a magnetic tunnel junction device. This is a low resistance state. This is a high resistance state. So you can reach both low and high resistance states, use a field, which is this green curve, or using a current. So you can access both states to show this really works, just like a magnetic field, but you can use a current to switch it. Then it just makes all the advantages I showed earlier, so it's more scalable, and also you can make the structure simpler, so you can pack more. So this is the density of your memory. Okay, so here is a chart to show there are many memory technologies. Some are matured already, some are emerging. So where does this STT-MRAM fit in this landscape? So what I have here is on the y-axis is the write endurance. That means how many times you can write the device before it breaks down. And the x-axis is the write cycle time, means how fast you can write this device. So we have matured technology already. So there's hard disk drive, and then those are the flash. And then you have DRAM and SRAM. So those are, you can see, if you look at it in terms of endurance and also in terms of this write speed, there is a huge empty space in between, right? In terms of speed, this is 2 orders or 3 orders of magnitude slower than DRAM. And in terms of endurance, it's really 10 orders of magnitude in terms of difference. So that's why in the past 20 years, I would say there are many emerging memories. I just listed a few, which were studied more extensively. So this is this resistant RAM, phase change RAM, and the ferroelectric RAM, and also STT-MRAM. And you can see in terms of the intrinsic switching property, STT-MRAM is the only one that's get close to SRAM and DRAM. And in this chart, you always can glide through this way. It's hard to make them to push them up. So one thing I want to point out is this ultimate memory device performance is really limited by their switching mechanism, so the physics. For example, when you think about the DRAM, when you think about it, it's fairly bad memory because it leaks like crazy. Every millisecond also you have to recharge it. But if we can find the application, then it's still okay. It's still the main working memory. So because the mechanism is you charge your capacitor, so there's inevitable there will be a leakage, right? So that's determined by the mechanism. And using phase change as another example, it is you are melting and quenching small material. So you are changing from the crystalline phase to amorphous phase to toggle from a low resistance state to a high resistance state. So there's inevitable that there will be wearing. But over time, the material they decompose, and the property will be different. So that really limits its endurance. That means you can really not write it infinitely. So a lot of them is determined by the intrinsic physics there. But a new technology takes a lot of engineering work. You can always show mechanism-wise, this is the limit, but you really have to put into the work to make everything happen so they can achieve their potential. So when STT-MRAM first came out, people were very excited because based on the physics, people think that it will be able to replace the whole landscape of the memory because it's also non-volatile, right? When you talk about DRAM, it's volatile, and the flash are non-volatile, and HDD is non-volatile. So you really have one non-volatile memory, which will give you the endurance and speed as good as the DRAM, and then it's non-volatile. So you really expect to replace this whole memory landscape. So people called it a universal memory to begin with. And there were a lot of excitement, try to make a universal memory. But I mean, after 20 or 10 years, people realize that that's just too ambitious. So the first entry people were trying to do is to replace the standalone DRAM, which you know it's like gigabits density and very densely packed. And I mean, I think many companies spend a lot of time on that. And right now, I don't know if I have that slide next. Yeah, OK. But right now, I think the wheel has changed a little bit. So for any technology, you have to find the right entry point. You cannot have a bar that high and then try to meet it to begin with. So what the industry, I think, settled down in the last 5 years or so is this kind of vision. What will be the MRAM product people should be focusing on as an industry? First, I think people just forget about the standalone for now. So we are going to do embedded. When you have a E there, it means embedded. So standalone and embedded, the difference is for the standalone memory, you just buy those strips and then you plug it in. There's nothing else, and it relies on the I/O to make the communication. Embedded means you have to go with the same flow on the same chip, everything with your logic. So that exposes some new additional requirements, very engineering part. For example, if you do logic right now, the process temperature is 400 degrees C. So they have standard process for your insulator, all those steps. So that means your magnetic material has to be able to survive all these process steps. And the magnetics actually does not go very well with the temperature. So right now, the standard industry standard for embedded process is about 400 degrees C. This is expose some challenge to MRAM. But with the embedded, usually you don't need high density. The requirement is a little bit less in terms of density. So you do gain something by going to embedded. So what people see right now is they see two kinds of memory. One is called flash-like embedded memory. This is to replace the embedded flash nowadays we have. And this one is really on the horizon. I think we are expecting to have a product in a year or two. And the second one is really further away, and this is to the so-called SRAM-like embedded MRAM. This one emphasizes on speed. So for example, for the flash kind of replacement, if I go here, so there is a huge margin, right? So you can do 10 nanoseconds with STT-MRAM. You are competing with something like 1 microsecond. So there is a huge window in between. So if you can do 30, 50 nanoseconds, you are way better than flash already. And in terms of endurance, you can also see there's a huge gap. So it's a kind of like an easy target to do with the embedded flash. But if we want to compete with the SRAM, you really have to push everything. So that's, I think, what the industry had in mind. And as I said earlier, for the embedded flash kind of replacement, you probably will see it in a year or two in the real product. And at IBM, our focus has always been on the SRAM-like embedded, because we really do things 10, 15 years ahead of time. And as mentioned earlier, so for the embedded flash kind of application, I mean, you emphasize on retention, but you don't really emphasize that much on speed. Well, for SRAM kind of application, because you want to write really fast, so speed is more important. So this is the desired key device performance. So when you start to work on MRAM devices, what do you really care about? So I picked out three the key ones to talk about today. The first one is obvious. So you want a large TMR. This is what I explained earlier. You want to have a read margin, right? When you have millions of the billions of bits, you want to still be able to separate the resistance so you can read them. And one way is to narrow down the distribution. The other way is obviously to make the mean to be further apart. So this has always been a goal to achieve, and I will talk about one of these materials breakthroughs enabled this to not be the leading issue. And then also because MRAM will come in as a non-volatile memory, that means it has to be able to retain the information for a certain period of time. So the retention actually depends on your application. If you have an application you write every 30 milliseconds, then retention requirement will be really low. If you want to retain the information for 10 years, then it has to be really high, right? So those you have to be adjust by the specific application. And there's nothing for free. So retention and this write current always coupled together. Where if you want something to be, can retain information for a long time, you have to pay something. What you pay is current. And I will also talk about what the materials breakthrough to enable to improve both at the same time. So there's a number we quote is we call it efficiency. Basically for every KT of thermal barrier, how much current in terms of microamp you pay. So this is more a fairer way to compare the device performance. And I will also use those metrics later on in some of the slides. So now let me move on to the materials breakthroughs. That was I think I picked the top 2 in the industry to link back to the read operation out of the write operation. So the first one, I will talk a little bit about the tunneling magnetoresistance. So this phenomena comes from the effect. I mean, in your magnetic materials, you have a majority and a minority spin, and at the Fermi level, there are some imbalance in terms of density of state. So ignore the details. So the net is you can actually predict what kind of MR you are getting. So this depends on this spin polarization, which is the imbalance. So this spin up and spin down density of states at Fermi level. And what was I going to say? I'm drawing blank. Let me think what I want to say on this slide. And so these numbers are okay. So for a typical ferromagnetic metal, for example, cobalt, nickel, and iron, so the spin polarization itself is somewhere around 0.6, 0.7. So it gives you a TMR about 50%, even for the intrinsic. And if once you have some interface defects, then the MR is even lower. So this is what we are facing, and for many years, this is what we were facing, but people still trying to make some product out of it, even with the TMR fairly low, 30, 40%. The first generation of magnetic tunnel junction actually was used in the recording head. They used magnetic tunnel junction to realize this read operation, and they have a little bit lower bar. And the first generation of field MRAM, they also used the TMR about 60, 70%. So back then, the only known tunnel barrier, which you have a very good quality tunnel barrier because the interface state determines how much loss you will have for the spin polarization. So the well-known barrier before is aluminum oxide. So it's an oxide that people know very well, and people know how to grow it well. But it limits your TMR to about 60, 70% at room temperature. So it was until later on, about early 2000, Professor Butler from Alabama University, he had this theoretical paper. He said, instead of using amorphous aluminum oxide barrier, if you can make a structure which is used with crystalline MgO, and if it's a texture, in his case, I mean, it's a theoretical paper, so he can put the atom wherever he wants. So it's a 001 oriented MgO. And for the electrodes, if you just use this common ferromagnetic electrodes, iron in this case, and if you can align them perfectly, which you can do, right? If you do epitaxial grow, then you would expect a TMR larger than 1,000%. And one of the good thing about the material system is MgO and iron has a very good lattice mismatch. If you just rotate the cell by 45 degrees, so the iron and oxygen almost align perfectly to each other. So it is possible to grow something epitaxially. Right? Sometimes you see some proposal, the structure is so different that there's no way to make the epitaxial. So in this case, actually, it's a very good system. People can give it a try to really make this structure. So 3 years later, so in Nature Materials, back to back, so there are 2 papers talking about this structure following this guidance. And one is MD Brom, MgO substrates, and then you have iron, MgO and iron. They really see, about 200% TMR at room temperature, comparing, to 60 or 70%, which is the industry has been struggling with. And also, so this is MBE Brom result from a group from Japan. And the same time, so our colleagues from IBM Store Parking also had published a similar result using this MgO crystalline tunnel barrier and some cobalt iron free layer. And they were also able to show about 100%, 200% TMR. And these fields were made by sputtering. So that really made a big difference, right? For MBE, you can make epitaxial films on single crystal substrate, but not everybody has access to that. Once you can do sputtering, they really open up a lot of opportunity for everybody to try. So this is the TM picture to show, even with the sputtered film, they are expected to be polycrystalline. But for MgO, it has a very, very strong texture. So it's textured 001. It's not really, it's not single crystal, but it's strongly textured, and it works even with this strong texture. So since then, there is a really computation on how high the TMR you can push it to, which is very what we often see in the field. And then you can see really over the couple of years, people were able to really push it to about 500 and 600% at room temperature. I think the record is about 600% at room temperature. And then we said, OK, there's really enough for this application. And nowadays, I mean, for the scientific papers, they have all sorts of tricks to try to make the number as high as possible. But for the industry, in terms of application, nowadays, I mean, people use 100 to 200% with this similar structure. And those are really the key elements people have found, what matters to make the TMR high. So first, you have to have this well-textured MgO tunnel barrier. And then you have some highly textured BCC structure, cobalt iron or cobalt iron boron, those things to really match the lattice. And then you also need to eliminate some of these low spin polarization elements, because when you anneal your sample, right, as I said, for the embedded memory, you have to do 400 degrees C. When you anneal, you can see all things happen. So elements diffuse. So you want to eliminate those things that hurt your TMR. So I think that this is a really good guideline. So you can really move from the ideal structure, iron, MgO iron, and move to something more practical, as long as you know what we are doing. So in terms of this, the first requirement is largely satisfied when we moved to this MgO tunnel barrier. And so now I will talk about the writing part. So then this will lead to another breakthrough in the field. It's these cobalt iron boron-based materials with the perpendicular magnetic anisotropy. So let me explain that. As I said earlier, this current and the retention, they are coupled together, right? There's nothing for free. Higher retention, always higher current. So what is the way to maintain the retention while still reduce the current? So there is actually a big knob in the materials. So if you have a magnetic film, you can imagine, so this is a tri-layer film. This is my tunnel barrier. And the magnetization can either lie in plane or they can lie perpendicular to the surface. So usually the magnetic materials is always lies in plane because of the shape and anisotropy. So these are details, just ignore that part if you don't understand yet. So most of the material system, they have this so-called in-plane magnetic anisotropy, meaning the magnetization is really lies in plane of the film. So when you do the calculation, and the physics is very clear. So if you have, imagine so this is your magnetization, it's in plane, your free layer. So when you start to switch it, it has to process. Right? So there is some moment of time, it's really tilt auto plane. So then this movement gives you really an extra term in terms of the current, so how much current you need to tilt it auto plane. And this is some add-on term, which is very large. But in terms of stability, that does not really count in, because in the in-plane field case, what you care about is lining this way or this way, give you this energy barrier. So you go this way, this is the energy barrier, then you drop to this direction. Anyway, so the net is you pay a lot of extra, but you really don't in current, but you really don't gain it in terms of the retention. And in the perpendicular case, if your moment is pointing up, when you process, it's very uniform precession. And you don't need to overcome a large term because it's perpendicular already. And here you can really see the current you pay to switch it really scales with your retention. So it's clearly a much more efficient system. So people knew this very early on because it's easy to calculate. But people cannot find a material that fulfills the other requirement to a lower switching current. So now let me go to some of these equations. So for the TMR, you want as high as possible. So I mentioned this already. So you need a material, it has high spin polarization. And if you look at the current, so it clearly scales with your EB, which is your retention. But there's also another term. This is so-called Gilbert damping. So it's directly linear relationship. So if you want to lower the current, you also want a material has very low Gilbert damping. And then, of course, this is your EB here. So basically, if you look at the material requirement, you want something which has a very strong perpendicular magnetic anisotropy, because that determines your thermal stability in the end. And you want something that has high spin polarization and also low damping constant. And with the existing materials people looked for many years, it just does not exist. Either they don't have the high spin polarization, or they don't have a low damping, or they have some other problem with the temperature stability. So many years, people know this is the direction we should go, but it just didn't happen on the materials level. So that's until about 8-10 years ago, where this was discovered and also published by two groups simultaneously. One is from the group from Tohoku University, where they found this material. It's cobalt boron, which people have been using all this time for implant stacks, but it was just much thicker. So they were 30 angstrom for the implant case. Now what they found, if you just thin it down to below 10, it's 9 angstrom, then it goes perpendicular, because there is some interface anisotropy there. I mean, it scales with the thickness. So this is the paper they published in Nature Materials. First time they show just use the old cobalt boron people have been using all these years. I mean, as long as you thin down, you go perpendicular. And actually, we had the same discovery in IBM, but we instead of publish it, we patent it, but it's the same result. So this is the first time people were able to show that you can make perpendicular tunnel junctions, and there are results following to show if there is really an advantage when you compare to the implant tunnel junctions. And here's the result we published in APL and also in our IEDM paper. So here's the comparison. So this is switching speed going up. This is the current you have to apply. And you can see in both cases, perpendicular versus implant, if you want to switch something fast, you have to give it more current, right? That's the picture I showed earlier on. And if you compare the perpendicular to the implant junction, so their EB thermal stability is roughly the same. For the same speed, you can see the perpendicular junction do give you a factor of 3 kind of improvement as predicted. And another thing is you look at the slope. So if you want to switch faster and faster, how much current you have to pay is also much steeper. So it clearly shows this advantage. And then there's other thing, in terms of the rise stability, also there's some advantage. This one I will go into later on. So it was very clear. So if you can move from implant to perpendicular, you get all these benefits you were expecting. So that's from then, I think the whole industry shifts to a perpendicular tunnel junction, both the industry and also the university people. I think because they have very well-published material. For example, in the APL, we also give all these material details, which is sputtered, so everybody can just go ahead and start to make some by themselves. And it really helped the field to move forward. So here is some of these problems. So I mentioned earlier, so the trick is you just thin it down from 30 angstrom, which is fairly thin already. Now you thin it down to 9. And one of the problems is if you scale down your device, you can imagine the magnetic volume will just shrink significantly. So what we did in 2012 is so we checked this thermal stability and also the current with smaller devices. So the paper I showed earlier was on large junctions, 100 nanometer junctions. So we really use E-beam and try to see if they behave the same when you scale it down with these perpendicular tunnel junctions. So the current does go down as you imagined, because you should be scaling with the area. So down to 20 nanometer, that's still true. But the EB, as you can imagine, your volume is getting smaller and smaller, so it just drops to something acceptable. So at 100 nanometer or 60 nanometer, you are about 60. This gives you roughly 10-year retention. And if you go to 20 nanometer, then below 30 almost. So it's not going to cut it. So then one of the thoughts is there are a lot of understanding and also theoretical papers to study where does this perpendicular magnetic anisotropy come from. So the conclusion is it comes from this orbit hybridization of cobalt iron with oxygen. So this is, there are a couple of papers to show that result. And then the natural thought is now you have one oxide interface to give you this perpendicular interfacial anisotropy. If you have two interfaces, you will just double this interfacial anisotropy. You will be able to go to thicker cobalt and boron. So this is what people have tried, and this is really worked. So you have MgO tunnel barrier now. You also have some sort of oxide cap. So you can also have interfacial anisotropy coming from the top interface. And this is really what the industry is doing right now. I will skip this one because I think I'm a little bit short on time. So basically, nowadays, what people are using is this kind of structure, but with a double oxide interface. So just to summarize, on the TMR side, the solution right now is a crystalline MgO tunnel barrier plus these cobalt and boron-based electrodes. And for the writing part, the solution is cobalt and boron-based free layer with perpendicular anisotropy, has low damping, and also this double oxide interface. So this one, we think we can allow us to push down to about 20 nanometer with still fulfill all the requirements. Further down, we are still looking, or we need another material system also fulfill all these properties, but it has to be able to support, have even higher magnetic anisotropy, so we can really allow us to scale down further, down to 10 nanometer, for example. But this one does not, we don't have a solution yet. So now let me move on to some of the work we did at IBM, try to reduce the device switching current. So as I mentioned earlier, at IBM, for 10 years, our focus has always been fast switching and also lower switching current. Because for us, we need an embedded solution to replace, for example, embedded DRAM, and we need this high speed. So that has always been the goal for us. So I will show you what we have done. I'll give you two examples on the research work. So this is the two I'm going to show you in the following slides. So we focus on 10 nanosecond switching. I mentioned earlier for the embedded flash replacement right now, the target write speed is somewhere around 30 to 50 nanosecond. And for the first generation of embedded SRAM, it will be somewhere around 10, maybe a little bit less than 10 or maybe 10. So I will show you the data on the 10 nanosecond switching. So the first research work I will show is on a new concept we tried at IBM. It's called the double magnetic tunnel junction, which I will explain in the next slide. And also the materials optimization to improve the write reliability. So this is, again, back to some of the basics. So one thing I want to emphasize is, so this is the picture I showed earlier, where I said, if you want to switch something fast, you just have to give it more current. So here it's more like analytical, it's more obvious to see. It's y-axis is the switching speed, and the x-axis is this switching current. So this is your critical current. And obviously, if you want to write something faster, you just have to give it more current. This slope can change, though, as a function of material. It is something you can't optimize. So if you want to go from 30 nanoseconds to 10 nanoseconds, you always have to pay something. But how much you pay, you can engineer. So the first concept I have is for the double MTJ. So this is the single MTJ structure I showed earlier. So you have one tunnel barrier, you have a free layer, you have a reference layer. And how you switch the free layer is, so the electron carries the angular momentum and transfer the free layer, then you switch the free layer, you create a torque. And then, a naive thought is, what if you have two reference layers? So then you have spin torque coming from both interfaces, then you just double the torque, then you will reduce the current by a factor of 2. And on the right is some calculation my colleague did, and this was published last year, to really show, so this is the y-axis is the improvement in terms of the current. So how much you can, the single MTJ versus double MTJ, how much does the current, how much the switching current scales when you go to double MTJ. And the x-axis is just switching speed. So what he has shown is, actually, in the intuitive picture, you will think you get a factor of 2 gain. But when you really calculate it, it's more than a factor of 2. There are some details there, but if you want to know, read this paper. But the general message is, if you do go to double MTJ, you expect at least a factor of 2 improvement, if you can make the structure. So this is some of the results we had. So now you have 2 tunnel barriers now. Before, there are 2 states, resistance states. Now you have two barriers, so you can have a combination. And then if both of the barriers are alive, you can actually have 4 resistance states. And this is a characteristic of double MTJ. So if you make a device, if you see 4 resistance states, you know both barriers are alive and contributing in terms of the TMR. And here is the TM to show these 2 white lines are the MgO, the 2 tunnel barriers. And here are some of the results. So this is the device diameter versus this efficiency I was talking about earlier. Basically means for every KT, how much microamp you have to put in order to switch your device. And then, over the size we studied, basically, this is the size range we are interested in, 35-ish. And you can see there is roughly a factor of 2 improvement as expected. And also there are some advantage in terms of this operating window, what we called. Basically, the voltage you need to write your device versus when it breaks down. You want them to be further apart. So this is also showed there are some advantage. So this is the single MTJ case. For a 14 nanometer junction, you only have about 0.2 volts. But for the double MTJ, you have about 0.7, 0.8. That's because of the two tunnel junctions are in series. So it looks all good, but the thing is, it's very the structure-wise, it's very complicated. So this is more like a demonstrative concept to say if you go from single MTJ to two double MTJ, there is a factor of 2 there you can gain if you really need it down the road. I will skip this page as well. Then let me move on to the second part of the work from IBM. This is to improve the reliability of writing. Let me explain what it means. So this is the equation of switching speed. So this is switching speed as a function of current. As we said earlier, if you want to switch fast, you have to give it more current. There's also another term here. This is this theta 0. What it means is, so this is your free layer. So it's sitting on the north pole. If it's perfectly aligned with your reference layer, there's no switching, there's no torque. Nothing will happen. So this is one of the fundamental flaw of this whole memory. Right? You relies on the thermal fluctuation to knock it off the north pole, then there's an angle, then it starts to switch. But this number, this theta 0, is random. At any given time, it can be a different number. So that means even if you give it the same current, the switching speed will be different. So for every given current, at a given time, there's a probability of switching. Right? So this is what we call the right arrow curve. So basically, if you want it to switch fast, or more, you have to give it more current. But if you want to switch it more reliable, so this is the error rate. Going down means it's more and more reliable switching. So you also have to give it more current because of this randomness of the initial angle. And here is a typical curve, what we measured on the device level. So first is the y-axis is the error rate. So if you see an error rate of 1 in -6, it means if you write 1,000,000 times, you will see 1 error. Right? 1 in -9 means if you write 1,000,000,000 times, you see 1 error. So going down means it's more and more reliable in terms of writing. And so I have the 10 nanosecond switching curve and the 50 nanosecond switching curve. The first thing is, at the fixed error rate, if you want to write fast, you have to pay more in terms of current. This is what we talked before. And at the same switching speed, if you want them to write them more reliable, you also have to pay more current. So now when you talk about application, there's a certain error flow you want to hit. Different applications, they can be 1 in -6 or they can be 1 in -12. So that's also very different. So when you talk about the current, what you really care about is at what error level, what current you need. Right? So in that case, you can imagine there are different ways to improve it. One is you can this whole curve can move in, or you can just make it more steeper. In both cases, you will improve your switching current at the given error rate. So this is some examples of the different stacks. So the materials can play a big role. So those are 14 nanometer devices. So this is right arrow rate curve. Again, so this is measured down to 1 in -6, means 1 arrow when you write it 1,000,000 times. And the different colors, so on the left side is right 0. So you try to get to a 0 state. On the right side is the right 1 state. And the different colors are just different pulse width. So from 5 nanosecond, the red, all the way to 200 nanoseconds. So it goes in. And for the 10 nanoseconds, so this is the green curve here. So this device shows it can write at 5 nanoseconds and still hit this error floor. And on the right, it's similar curves, but the color are a little bit different. So the red is different. It is the slope for the 10 nanosecond. If you compare the green to the red, the green is steeper. So for the materials, you can do all these tricks to make it steeper or shallower, or you can push in the whole curve, as well. And here it's more obvious. So you have 2 different stacks. So these are all 10 nanosecond switching. We measured past the 1 in -9 error floor means it's less than 1 error when you write it a billion times. And the two stacks, you can see the slope can be very different just by engineering the material itself. And we also took the devices to see in terms of scaling behavior, how does this, we call the right error rate curve, changes as function of device size. So again, in all these plots, the red is the 10 nanoseconds to focus on, 40 nanometer, 25 nanometer, and down to 11 nanometer. So we can still go to 1 in -9 kind of error floor with a 10 nanosecond pulse, and the slope actually does not really change much. So there are data from other people to really show, I think in terms of the physics, it works down to 10 nanometer. But this device, if you look at the EB now, it's like 30 KT, so it's clearly too low. So as I mentioned earlier, down to 20 nanometer, I think this material system will get us there. But beyond that, we really need some materials breakthrough again to enable those small devices and still be stable. I think that summarizes the technical part. Now I want to give you a brief view on where we are as a technology. So first, there are products on the market already. So the standalone 256 meg product exists already. It's a standalone memory. And actually, the IBM system actually used this already as a buffer memory. Yeah, in our systems, this announcement from August. So the product from Aerospin is standalone. What it means is, they may use a low process temperature other than 400 degrees C. And for the product in development, this one I mentioned earlier, so when people just started, we were very ambitious. We were shooting for a DRAM replacement. That's like 7, 8 years ago. So those are some joint efforts, a big effort actually, between SK Hynix and Toshiba. And they were trying to make a gigabit STT-MRAM standalone. And those are some of the IEDM papers they published. Right now, I think the conclusion is I don't think it's going to really appear. So they tried, it's just not there. They can do some demonstration, but there are plenty of problems. And DRAM just keeps scaling. So there is really no winning ground there for standalone MRAM. The bigger effort is on the embedded MRAM to replace embedded flash, as I mentioned earlier. So this is a paper from Samsung. So these are 8 meg embedded with their 28 nanometer logic. And I think they are really working on a bigger size, probably 32 meg. And you will see it in the product, hopefully, in a year or two. And here is really the MRAM in the news. I mean, if you follow it, they were seeing all these major industries, Global Foundries, Samsung, TSMC, and UMC, the 4 leading foundries. They are all putting a lot of effort into MRAM, and all of them are announcing some kind of risk production in a year or two. So we will see if they really come out. And here is, again, these different types of MRAM envisioned. As I mentioned earlier, you will probably see the embedded MRAM as a flash replacement fairly soon. And then the research focus right now is all on this high-speed application. And here is basically all these companies, they are working on it, all these major foundries, and plus many startups, actually all over the world. So I think it is really coming out. And hopefully we can also make the second phase, which is the high-speed application. And with that, I will summarize. So this is a brief summary to talk about the switching current, which we really care about, which I also talked about already. So you have your critical current, and when you go to 10 nanosecond, you need a higher current in order to get the speed. For the same speed, if you want to have a deeper error rate, more reliable, you need to give it more current too. And in the end, this is the right current. We have to be higher than whatever you required. And on top of that, just thinking about the millions of bits, they have to, to be all below this one right current you set. The distribution, everything has to line up. So that's what we are fighting against. And for the MRAM technology, the first generation, I think, is coming out fairly soon, in a year or two. And the research work is really try to meet these high-speed requirements. And the new switching mechanisms or new materials or new design is really needed for the next generation to really work. That's all I have, and thank you for your attention.
Thank you, Dr. Hu, for a very interesting talk. And now the seminar is open for questions from the public.
Thank you for a nice seminar. Just a quick, more practical question. Some of the newer materials that you have been investigating include magnesium and iron. So I wonder to what extent those can be silicon compatible. To what extent those can be introduced in a silicon fab.
Those are interested in the silicon fab.
Really?
Yes, in the manufacturing tool. I mean, they do worry. You worry about contamination, right?
Yes.
Yeah. So for the iron, it's a big contamination, but they do crazy cleans of all sorts to get rid of those materials. Actually, it's not a problem, even in the foundry environment, even in the sound foundry environment.
Also with magnesium, which I have a sense that moves around very fast.
MgO, I mean, once it's oxide, it does not, right? Iron, it's really concerned. Iron, nickel, cobalt, they don't like any of those, but they have really have gone through very different ways to try to clean it, or they can bury it. There are some MRAM designed tools, so they only show up there. Then they bury it under, for example, silicon nitride or something. So during the process, you don't see them anymore. Or you have some way to clean them after those magnetic related steps. But it's a very good question. I mean, people fight to resolve those problems in the fab.
Anybody else? Well, I have a practical question. I got interested in your statement that at some point when you had this perpendicular structure, that there was this very fast transfer of technology between the academia and the industry. And I was wondering if you could comment a little more on that, and if that's like a very fortunate occurrence, or that actually happens quite a bit in IBM, or maybe some challenges about scaling up something that happens at the academic level.
Yeah, so I will try to answer the question. I hope I get it correctly. So what we have seen is in the industry, we do a lot of research work. So the advantage I think we have is we know exactly what problem to target for, right? So like for the academia people, sometimes it's not totally clear. For example, everybody push for the highest TMR. You can show 600, but if you're, for example, the resistance, when you thicken up the MgO, the resistance goes up, the TMR goes up. People, they don't really care, academia people, they want to push the highest number of TMR. For us, they can show 600, but when we really use it, it's only 100 or 200 because we have other constraints. But I think it's also good, for the university people to really think out of the box to push the limit, and the industry people really scale down to what is really practical to use. And so that's one example. And the other example is this system you were just talking about, right? So we try to solve the problem. We know exactly what the problem is. And when we find something, usually we don't publish them. We file a patent really to protect our own IP. And it's not really helpful in a sense, right? You have a very small group of people working on this problem. You have a breakthrough. But sometimes you really need a lot of people to generate the idea and do it together. But we are just not, we are constrained. We cannot really do that. Once the university people publish it, it's really, everybody can jump onto it. Then you make more progress. Yeah. So it's a kind of like a dilemma. I don't know if it will work better if we really have universities groups really have a very close relationship with the industry, right? You have this joint study agreement, those kind of things. Whether it will be kind of break the barrier. I know there are things like that happening, but a lot of times the discovery is unpredictable. You can have a discovery in the industry, but you don't have this joint study agreement with someone, to just still have to keep it secret for years. So I'm very glad this one, it just happened at the same time, so we didn't really lose any time as an industry. But I think it's really a dilemma in how we collaborate more closely, so exactly what problem to solve. But I mean, it's also, it's like a two-edged sword, whatever you call it, sword, you call it, right? On one hand, those practical problems, you want the academia people to help. But on the other hand, you don't really want to limit them either. This is the nature of the research, right? You don't really know what will get you there a lot of the times. So yeah, I think we need to think from both ends. What is the best way to use this, everybody's brain instead of this discrete effort. Yeah.
Maybe also in this direction, what do you think about the spin-orbit torque switching as compared to spin-transfer torque switching?
I know this question has to come up somehow. From a practical point of view, I think one of the big differences for the people who are in the audience who are not familiar with the field. So what I showed for the spin torque MRAM, one of the advantages is the structure is very simple. It's a two-terminal device. You have MTJ and you have transistor. That's all. Structure is simple, so that means you can pack them very densely. So the spin orbit torque, sorry, I forgot your name. Just asked. It's a three-terminal device. So basically, you send a current underneath your MTJ to write your free layer. Then the read, you still use the magnetic tunnel junction. So you already have a three-terminal device. So by itself, it killed a lot of application already. So you can already easily make an array as dense as a two-terminal device, right? And something I think they have to show also is efficiency-wise whether it's any better. I mean, power-wise, people have shown it's better. You can write it very fast. The big advantage is now you can imagine your read and your write are separated. So you use the current underneath in the wire to write your free layer when you use the magnetic tunnel junction to read it, right? So one of the things I showed earlier is the operating window is so the write voltage and the breakdown voltage has to be further apart. So if you can separate the read and the write, then there's huge advantage because when you read, you use a very small voltage. You don't really worry about breakdown. The write, you use a different path. But I think in terms of efficiency, people haven't. So then, in terms of efficiency, people haven't really showed any advantage for this SOT device. And I know people are moving from in-plane to perpendicular. The in-plane again. Density-wise, I just don't see how you can make it, right? If you have to go to perpendicular, then the current is much larger. So there's all these dilemmas. So we are really keeping a close eye on the development, but it really needs some breakthrough to be really can compete with this two-terminal device at this stage. I think it's a very good university project. That's one example. It's a very different mechanism. It solves some of the problems, but it causes some other problems. And then what is the middle ground? Yeah.
Okay, we have run out of time, but let's thank the speaker once more.